physicist of today is Johann Carl Friedrich Gauss. He was born in 1777 and died in 1855. Gauss's law relates the electric field at points on a closed Gaussian surface to the net charge enclosed by that surface. It's important to realize that a Gaussian surface is not a real physical surface. It's a surface that we construct in order to help us solve problems. So if we take a look at this example here, let's pretend that we have some enclosed point charge with electric field lines that are emanating from it. We might construct a Gaussian surface around this point charge in order to help us solve a problem. So let's say in this example that these field lines here represent a charge Q. What if now instead we had this number of field lines? What could we say about the charge that was enclosed in this situation if we didn't know what the total charge was? But we knew in this case this many field lines represented a charge Q. The answer is that the charge enclosed by this Gaussian sphere would be 2Q. And the reason is because out of this Gaussian sphere we actually have twice as many field lines coming out as compared to this initial example. What if instead we had this situation with our field lines? What could we say about the charge enclosed in this case? In this case, we have half as many as the original example. And notice that instead of the field lines pointing outward, they're now pointing inward. So not only is our charge reduced to half the original charge, but the electric field is in the opposite direction. So instead of a positive charge, we have a negative charge. So using the electric field lines, we can tell something about the charge inside a Gaussian sphere. The next concept that we need to know something about is the idea of flux. The Latin word for flow is flux. The amount of electric field passing through a surface is called the electric flux, and is represented by the Greek letter phi. Only the component of the electric field that is normal to the surface contributes to the flux. So the flux is equal to E cosine of theta times delta A. So in this example here, where we have a vector that isn't perpendicular to the surface at this point, but is instead at some angle theta with respect to the x-axis, where the x-axis comes directly perpendicular from that point. So it's normal to the surface at that point. Only the component that is along the x-axis contributes to the flux. And so that, as you can see, is in this case has a magnitude of E cosine theta that just comes from trigonometry. We have a compact notation for writing this in mathematics. It's called a dot product. And that notation is represented here. So if I go E vector dot delta A vector, where delta A vector, it represents essentially this little element, delta A here, which is just the element of this larger area sheet. So if we want to find then the total flux that's given off by this entire area, we integrate. So our total flux is then just equal to the integral of E dot dA. In order to use Gauss's law, we need a closed surface. The net flux on a closed surface is given by this integral here. And so to represent a closed surface, what we do is we put this little circle around the integral. And that represents the fact that we're integrating upon a closed surface. Notice here in this example, these closed surfaces can be very complicated. And we do have some different conventions. The inward piercing field is a negative flux, and an outward piercing field is a positive flux. A skimming field, so one that is parallel to a surface, is a zero flux. So let's take an example. Let's calculate the flux through a closed cylinder in a uniform field. What is the net flux through a closed Gaussian cylindrical surface of radius r that lies in a uniform electric field E with a cylinder's axis parallel to the field as shown in this figure. So the first thing we need to do is find the net flux by integrating the dot product. However, we can't do that in just one integral. We need to break it into three pieces. We need to integrate each of the end caps, end cap A and end cap C, and then this center portion separately. So our integral is going to be the integral of E dot dA over surface A plus the integral of E dot dA over surface B plus the integral of E dot dA over surface C. And we'll just take each of these pieces one at a time. So let's start by examining surface A. So the integral over surface A of E dot dA is just going to be equal to E cosine of 180 times dA. Again, remember, we only worry about the component of the flux that's perpendicular to the surface. In this case, fortunately, our flux makes an angle of 180 degrees, which is nice because the cosine of 180 is 1. So also notice in this case, since our vector is pointed our vector is pointed in the opposite direction of our E field, so we have minus E, the integral of dA. Since we're integrating over dA, dA is the area, it's the area of this cylinder end cap here, and so that area we'll just call area A. So we'll use A here to represent the area of the end cap. So now let's examine surface B. In this case, the angle between dA and E is 90 degrees. Hence, our dot product is 0. Thus, E dot dA is equal to 0. Finally, let's examine surface C. The integral E dot dA, again, just like in the case for A, is E cosine times dA. So this time, though, the E field's in the opposite direction, so we end up with plus E, the integral of dA. And so we end up with a plus E times A, where again, we're just using A to represent the area of the face of the surface of the cylinder. So let's put it all together. We need to add E dot dA for surface A, the integral of E dot dA for surface B, and the integral of E dot dA for surface C. So we have minus EA plus 0 plus EA. When we add that all together, we find that the flux is 0. And this is exactly what we would expect, because the flux that came in is the same as the flux that's going out. So Gauss's law relates the net flux of an electric field through a closed surface to the net charge that is enclosed by that surface. So why is it that we even have Gauss's law? Gauss's law allows electric fields of continuous distributions of charge to be found much more easily than using Coulomb's law. Also, Gauss's law is valid for moving charges, whereas Coulomb's law provides us only a very good approximation in that case. Gauss's law says that epsilon times the flux is equal to Q enclosed. Another way of writing this is epsilon times the integral E dot dA equals Q enclosed. So let me ask you a question. Which of these Gaussian spheres, the inner sphere or the outer sphere, contains more electric flux? Notice that Gauss's law tells us the electric flux is independent of the shape or the size of the Gaussian surface. It depends only on the amount of charge enclosed. Both of these Gaussian surfaces enclose the same amount of charge and the same amount of electric flux. In this case, the answer is each of these contains the same amount of electric flux. So let's take another example. Let's use Gauss's law to drive an expression for the electric field located a distance r from a point charge q. First, let's draw a closed spherical Gaussian surface a distance r from point charge q. Then we need to apply Gauss's law. So epsilon naught times the integral E dot dA equals Q enclosed. Since all of the electric field lines are normal to the spherical Gaussian surface, our dot product becomes epsilon times the integral E cosine 0 dA equals Q enclosed. In this case, E cosine 0 is just E times 1, and since E is a constant, we can pull it outside the integral. So we end up with epsilon times E, the integral of dA. Q enclosed, in this case, is just positive Q. In that case, on the right-hand side of our equation, we end up with just Q. Now, we just need to sum all the patches of the sphere. When we do that, we end up with 4 pi r squared. So that leaves us with epsilon naught E times 4 pi r squared is equal to Q. Rearranging the terms and solving for E gives us E is equal to 1 over 4 pi epsilon naught times Q over r squared. This you might recognize as Coulomb's law. This should give us a lot of reassurance that when we look at the case of a point charge, that we get back Coulomb's law. Now let's take the case of an isolated conductor. If we have an isolated conductor in which an excess charge is placed on it, that amount of charge will move entirely to the surface of the conductor. None of the excess charge would be found within the body of the conductor. And so what you can see here is that means if I were to take a Gaussian surface, if this here is a slice away of my conductor and it has an excess charge on it, and I were to take a Gaussian surface and cut away through here, what that means is that I would have an electric field coming out of one side of my conductor, but no electric field on the Gaussian surface that is inside my conductor. So no field lines are going to pierce through the internal end cap of that Gaussian surface. So for a conducting surface, Gauss's law would give us that epsilon E times A is equal to sigma times A. So E is equal to sigma divided by epsilon naught, where sigma here might be a new concept for you. Sigma is surface charge. So it's the charge per surface area. This is something we learned about in the last chapter. So let's take an example of planar symmetry. Find the electric field E at a distance r to the right of an infinite sheet of positive surface charge density sigma. The first thing you need to do is choose your Gaussian surface. In this case, a cylinder is the most advantageous. The next step is to apply Gauss's law. So Gauss's law says sigma times the integral of E dot dA is equal to Q enclosed. In this case, we actually have two surfaces that we need to take care of, because in a cylinder, you only have field lines that are normal to the end caps of the cylinder. So in this case, you have epsilon naught, the integral of E cosine 0 dA, plus epsilon naught times the integral of E cosine 0 dA. And this is equal to Q enclosed. And in this case, your Q enclosed is only on the sheet. And so the Q enclosed is sigma, which is your surface density times the area. And the area of your cylinder here is A. So again, here you will get from this first integral E times 1, which is a constant. And when you do the integral of dA will give you A. So you have EA. Similarly, the second integral is identical to the first, and so you will also get an EA from doing this integral. When you simplify this, this will give you 2e times epsilon naught is equal to sigma, and that is because you have an a in each of these terms which cancel out on both sides of the equation. Then you just solve this for e, and you end up with e is equal to sigma divided by 2 epsilon naught. This is your expression for a sheet of charge. This is the end of your video lecture for today. We'll see you in class.